Thank you, Pierre. So, hi everyone. Thanks to be there. It's my first talk ever in French or English or whatever. So, if I'm nervous, that's hopefully, I guess it's normal. Before I start, I will just make some excuses for the expert of Bitcoin. I will take some shortcut for everyone to understand the principle. So, I know that some of the Bitcoin experts may be offended by the shortcut I will take. I'm sorry. Basically, this talk is about de-anonymizing the Bitcoin network by regrouping addresses using public sources. So we'll start right away because I only got half an hour to make the talk, so I'll go right away. So first of all, what this talk is not about. Those questions, I heard it a lot. I have it every time I talk about Bitcoin, I have those questions, and seriously, I hate answering those questions because I don't have any opinion on those questions, mostly. I don't care, I don't know if Bitcoin will replace all currency. If you buy a cluster, that's your choice. Who is Satoshi Nakamoto? Have no idea that you have. Every sentence that starts with does empty guts, does something, I don't care. And is Bitcoin real money? It depends. So now, what is the talk about? It's about addresses, about blockchain, transaction, and what is the limit of pseudonymity. Because we tell that Bitcoin is an anonymous network, but it's not exactly it. So during this presentation, I'll try to teach you how to associate addresses to a possible entity, and then after use external sources of information to match a real person identity over a node of the network. And finally, we'll get a tool release because I'm pretty sure you just won't have the tools and try to use it at your own. So first of all, Bitcoin 101. As I said, I'll do some shortcut. So first of all, an address is your identity on the network. It's based on the public key. So basically, you generate a public-private key. You take your public key, you hash it, you encode it, and you get an address. So that's mostly it. So that's a simpler representation of a private key, a public key, sorry. And so far, I've seen 70 million addresses on the network. Now for the block and blockchain. A block mostly contains transactions. So when a transaction is created on the network, it is in the unconfirmed state. As soon as it's included in the block, it became confirmed. Depending, like I know for a Bitcoin expert, you have to wait some blocks to make sure that it's really still confirmed in the block. But for our purpose of the presentation, when a transaction is in the block, it's confirmed. The blocks are chained together, and they create the blockchain. So the chain of blocks that created and start creating the big registry of all the transactions is the blockchain, and a block is mined every 10 minutes. And as I said previously, new transactions are included in this new block created by the network, and they became in the confirmed state. So that will be in the transaction history forever, or at least for the time that Bitcoin exists. Transaction. So one thing to understand is a transaction is a money movement. As you do transaction all days in the real life. Well, Bitcoin is still the real life, but well, you understand what I mean. So basically, one thing is the input equals the output. So for example, here on the slide, if you want to pay Bob, so Alice wants to pay Bob, she will refer to previous transaction where Alice received money from Fred and Alice received money from Charles. And then she will say, okay, I received 2 Bitcoins on this transaction. I received 3 Bitcoin in the other transaction. Now I have the right to spend those Bitcoin and to send it to someone else. So basically, she will send it to Bob. So the output here will be Bob, 5 Bitcoin. 2 plus 3 equals 5. If Alice wanted to send only 1 Bitcoin to Bob, what she should have done is, for example, send 1 Bitcoin to Bob and 4 to Alice. So she's sending the change back to herself. So that's if you want to send money to someone, you basically send the money you want and keep the rest by sending it to yourself directly. So that's the important that the amount of input equals the output. As I said previously, Alice referred to previous transaction to say, hey, guys, I received money in this transaction back in the days. Now I would like to spend them. So she referring to output of previous transaction. So Alice said, okay, I have this transaction here. I received money in the output. Now I will spend it as an input in the new transaction. So that's it. So basically, she just to write that, okay, in the ledger, I have received money there. I now spend it and sign it in the new transaction. And to prove that I have the right to send it, and to prove that it's really me that have these addresses, I will sign the transaction, the input, to make sure, to prove you that I own the private key associated to these addresses. And fun fact, I have approximately 50. Other point, guys, when I was in elementary school, I think I missed a class where we're explaining numbers in English. I'm pretty dumb with number in English, I'm sorry. So 65 million transactions that have been seen on the network. So as I said previously, so input and output. So output is an amount of money that you want to send, and next to the hash of the recipient public key. So for example, I want to send money to Laurent next year. I take his public key, I hash it, and put 3 Bitcoin, the hash of Laurent public key. And when Laurent wants to spend the money he received from me, what he will do, he will take the hash when he received money from me. So we take the transaction hash, put it there, said he received money from me in this output. He will sign all the previous transaction with his private key and put his public key next to it for the network to verify that the identity, to verify the signature. So when the network verifies the signature, what's happened is the network take the public key, the network hash the public key and compare to the previous hash 160. And if it's matched, it says, okay, so that's good, so the public key match. Now I have to verify that he owns the private key associated to this public key. So basically, the network will take the public key and verify the signature that is made with the private key. And if the signature is good, he said, okay, so that's a good person. And he proved me that he had this private key. So I'll do a small recap here because I may have lost some people in the process. So basically, you have a private key, you hash it, you get a hash 160, you encode it, and you get an addresses. So that's important for my tool. So that's why I redo the diagram there. And the other is really like the exchange mechanism, the transaction mechanism. So as you can see, in the transaction 3, you got input that's referred to transaction 1 output and transaction 2 output. So I will take the first input, get the output referred, take the hash 160, encode it, and get the address 0. I'll do the other thing for the other one here. So I will take transaction output at index 0, so this one. I'll take this hash 60 here, I'll convert it to an addresses and get another addresses. So basically, if the transaction is valid, that means I was able to sign input 1 and input 0. Both of the input I was able to sign with the private key associated to those addresses. That means that possess, at a certain point, I was able to have those 2 private keys on my position to sign and to create a valid transaction. So I can tell that those 2 addresses belong to one entity on the network. So that's 2 addresses that belong to one entity. It could be a person, it could be an automated system, it could be a laundering scheme, it could be anything, but it belongs to an entity in the network. So for example, if in this slide, I have 4 transactions that I parse, and I found that addresses 1 and 2 was used together in a transaction. I found that addresses 4, 5, 6 was used simultaneously in a transaction, and 7, 10, and also another transaction that used 2, 4, 7. So basically, I can associate it like this. Okay, so that means that the person have the address 1, 2, 4, 7, because it reused the same addresses in different transactions. So by doing this, you're leaking the information that you have 1, 2, 4, 7. And you can do for all the node, and then merge it together and tell that that's all the addresses of an entity. So basically, you can regroup addresses telling that those addresses belong to an entity on the network. But I don't know, it's still anonymous. I still have addresses. I don't have a real identity that I have to get external source for that. So basically, the goal of the tool is to create a graph of the Bitcoin, of the blockchain. So I will take every block, take the transaction of every block, create a node using the input addresses of all those transactions, merge those nodes together, and finally, I will get a graph where a node represents an entity and an edge represents a money flow. That means money moving from an entity to another one. My assumption, as I said previously, I assume that if you use multiple addresses as input of a transaction, they belong to the same entity. That means that there's one special kind of transaction that are negligible, multi-sign transaction. So it's the same principle as in the company, you need to have 2 persons to sign a check for the check to be valid. So it's possible to do it in Bitcoin, but the number of transactions that use this kind of mechanic is negligible. So basically, we just don't crawl those transactions and assume that it does not exist because they are quite small. They are quite in small number in the network. And the other assumption is people don't know how to use Bitcoin and reuse addresses in multiple transactions. So instead of sending the change to a new addresses they created, they send back the change in the already existing address and reuse this addresses multiple times. That means that I can do like the merge that I explained in the previous slide. The tool, now the funny part, because I know you just want to hear the good story, and that's a good story. So basically, I become with a graph problem and say, oh, well, that will be complicated. It will be really, really complex as a program. I don't know if I will be able to do it for the NorthSec presentation. And finally, the graph problem takes me a day and a half. And the big data problem takes me until last week to figure out. So it worked well in theory. The data is public. That will be easy, right? You know, you have all the blockchain. You can download it from the internet. It's easy. It's public, and it's only node in memory. So that means that's an array of byte and integer. So that will totally fit in memory. Like I have more than enough memories. Well, I was wrong, as you can imagine. So idea number one: get a block from the blockchain. Take each transaction of this block. Take each input of the transaction. Get the reference output to get the hash 160. Calculate the Bitcoin addresses from this hash 60, put it in the graph, and finally watch it run for 3 months and flipping tables. So basically, first idea was wrong. Idea number two now. So I started over. Get a block. Take each transaction of the block. Take each input of this transaction. Decompress the public key in the input. Calculate the addresses for the public key because, you know, the hash 160 is just an hashing of the public key. And wait, those addresses does not exist. So all the addresses that I calculated, in fact, were never existing. So what I mean, I did something wrong there. So again, the table has been flipped. So idea number three, understand what you're doing wrong in number two. In fact, before converting it to a hash 160, you don't have to compress the public key. And do good code to grab the Bitcoin, like object-oriented, like linked list, Python, good code, everything was clean, was understandable. It was my best 100 line of code I made. Everything was clear. It was easy to follow. Find that your merge routine is linear. And I will still be crawling by now if I wouldn't have stopped this program. It would have worked, but I wouldn't be able to present today. So again, flip tables, idea number four. Yeah, that's something I do when I have problems. So, and I decided to revert the clean code. I did crappy code with hash map, hash table that was totally a mess, impossible to follow, but it worked. So watch the crawler, run the crawler for 2 or 3 hours, get the out of memory exception, said, okay, now I have big problems. So I cannot do it in linked list, and I cannot do it in hash map. I'm screwed, mostly. So another table and the flip. Idea number 5, realize that you were running Python 32-bit with a space limit of 4 gig. Decide to use Python for the 64-bit. Run it for 16 hours straight and get another memory exception. And this one was real. I exhausted my RAM of my laptop plus my swap file. So, okay, no problem. I'll use a DB. I'll just dump to DB. Like every 1,000 block, I'll just dump it into DB and then merge with the DB. I'll figure out how to make it. And my transitional DB just died, mostly. So I was still in a bad position. And finally, I was able to use MongoDB with multiple instances, like inserting each 1,000 block into the DB, wait for 24 hours, 24 hours, sorry. I know what I'll tell you. And finally, I was able to make it work. So the minimum system requirement for running the tools, like for crawling it, not the DB, for crawling it, it's 30 gig of hard drive, 32 gig of RAM, Python 64-bit for sure, 24 hours of free time. So are you willing to do it live? And 4 table to flip. That's really, really important. If you will not succeed it. So finally, the part that you want, the demo. So the tools like this. That's my tools. I know. It's the least impressive tool ever. So basically, what I will present today is, like, as I tell you, I was dumping it into DB. So I have the MongoDB on my computer. And we're going to have a real use case. So this use case is taken from Radio-Canada stories. Basically, they interview someone who has a crypto locker and lock all this file, and she had to pay to get back his video from her kids, and like the classical crypto locker stuff. The point is they didn't blur the addresses. So as you can see, or may not, if you're at back, you have like the kind of dense. You can maybe guess the beginning of the addresses. And since I have a DB, so I will able to find these addresses back. So we are doing it live. So basically, I will not scoop that. This one. So I have the DB there. So I have the DB. If I do, for example, I have approximately, like as I said before, 70 million entries in database. So I'll try to guess the addresses. So I'm sorry, I know you know I'm working on slide right now. Annexes, that's what I need. Okay, so the addresses that we found start with this command. I'm scooping it a bit in my presentation, but well, it's for the bed. So basically, the address is starting with 1LGNUV something something something. So oh yeah, nice, we found an addresses. That's really interesting. I crawled this addresses and it's associated with a node ID. I want to know if, for example, this bad person have other addresses that he's using. We'll see. So basically, I'll try to get for the node ID. So I will tell, get me all the addresses of this node ID. So basically, we got 4 other addresses that are associated with this person. Thank you, my groupies. So basically, what we can do now is we want to know how many money this crypto malware locker received. So what we know now is this people behind this crypto locker also at least 3 other addresses. So we'll go on a website and check for the addresses. Oh, this one I've received 11 Bitcoin. Oh, this one 2 Bitcoin. This one 2.5. And this one 49, so 60. So at a certain point, this addresses of the crypto locker received approximately 70 Bitcoin. And it was working in the time that they did it, approximately $600 US per Bitcoin. So approximately they received $250,000 with this campaign, at least. So what we can do next is, for example, well, okay, so I have like a use case, a real use case from ESET. They tell me, okay, we found those addresses, and like in the blog post, they said, okay, we discover crypto malware. By Heisert Martiner find it, it had these addresses. And also what the version that we got has these addresses. We think it's pretty sure that they are linked together. Well, we can confirm for real. So for example, if we take the node ID of the first addresses and find it, you see that the node ID is 1258538, and the other node ID, as you may think, and you're right, will be exactly the same node ID. So we can confirm for real that two addresses belong to the same person. So, and now what we want to know is how many addresses that this entity possesses as addresses. I'm really slow typing, I'm sorry guys. With 8. So we got over 160,000 different addresses related to this node. So basically, that's a laundering scheme, or that's an automated tools, or someone. And if like we want to go further, we can know how many money we have. But seriously, guys, I'm sorry, but I will not do it today because I'm continuing my slide. It's in the what's next. Basically, what's next for my tools is to release the crappy code that I told you before that you can crawl the network. And you can take the DB from there and continue crawling from now to like so the DB that will be available is made Monday, not this week, the week before. So you can continue crawling for this block and just go further, and you'll get all the database until now. So basically, that's all the group, all the transaction, all the node ID that represent a person, and the addresses that related to this node ID. As you can know, what you can do right now is to take every addresses, find something interesting on the internet using, for example, Google, and then find other addresses associated with the addresses that belong to the same entity. So basically, the version 2 will be the follow the money. So basically, I will crawl again the blockchain and get every transaction and do the money movement between the node. So you'll be able to know how many money does it move from one node to the other node, or how many money were sent into the big long-range scheme. And then from this big long-range scheme, is there any like amount of money that looked like the first that was sent? So we can say, okay, she was node number 1 here, send it to the long-range scheme, and then send it back to the node number 2. So we said, okay, that's probably the same person because it was as much money that is sent into the long-range scheme that is exit and going to this node also. So that will be in version 2 eventually, and it will be still available on my GitHub also. And version 3 eventually will get the collaborative tool so that people will be able to add comment on the node, said, okay, this node is probably this bad guy. This node is probably this person. This node is probably this system. And you'll be able to de-anonymize the Bitcoin network like this. So that's it for me. Do we have any questions? Do we have time for questions, or I busted? I'm pretty